So you've made your code look good, but can you make your code run good? Well, let's talk about algorithmic efficiency. So how quickly can you get the same job done? Well, it depends on what kind of algorithm you're running, right? So let me show you a simple scenario where I'm trying to find whether an item exists in a list. So that's called searching. So these are two search algorithms. The first one is bad, but very simple. This is called linear search. So I've got a list called haystack and an item that I'm trying to find in that haystack called needle. So one way you can actually find a literal needle in haystacks by picking up every single stalk in the haystack and saying, is that a needle? If it's not, put it off to the side or put it in the burn pile or something. Is this a needle? No. So you meticulously look at every single stalk until you find the needle. So best case scenario, first stalk you pick up is going to be the needle. Is that likely? It depends on how big your haystack is. Worst case scenario, the very last one you look at is going to be the needle. Okay, so that's the worst case scenario in that situation. So no matter what, you kind of can expect, on average, I guess you can expect it to go through half of the whole thing. So as your haystack gets bigger, the number of checks you have to make scales linearly. Okay, so if you have 100 checks, your average, 100 items in your list, the average number of checks is going to be 50. The worst case scenario is going to be 100. The best case scenario is still going to be 1. But that's kind of trivial. You can say that if you have 1,000 items in the list, the worst case scenario is going to be 1,000. So it scales linearly. It keeps scaling as the number of checks keeps scaling as the number of items in your list gets bigger and bigger. Okay, so let's look at the implementation of this algorithm. So I've got my stack called haystack for I in range len haystack. So basically, I'm looking at every single excuse me. I'm looking at every single item in the list. If that item is the needle, then return I. Okay, this implementation doesn't work if the needle is actually not in the haystack. I'm not checking for that. I'm assuming that it's in the haystack. So it is checking to see, is this the needle? Is this the needle? Is this the needle? And finally, when it is, it returns that position. Okay, so here's where my code is actually being run to test this thing. For I in range 100, I'm going to repeat this whole simulation 100 times. I'm going to repeat this whole thing 100 times. I can change this too to get more simulation runs, to get more trials in there. This is a pretty interesting function, time.ins. Let's see if it'll give me the doc if I just hover over it. Come on. No, I can do it over here. Import time, help time.time ins. So this is the current time in nanoseconds. That's a lot of seconds. So I need to change that. Nanoseconds. So nanoseconds, that's 1/10⁹ of a second. Okay, a lot of those, 1 nanosecond since the epoch. So if I did time nanoseconds, that's going to be a ton of nanoseconds since the epoch. What is the epoch? The epoch. It came from 1970, so it's about this thing called Unix time. So basically, the Unix epoch was the turn of the new decade, January 1st, 1970. The reason for that is because Unix, this operating system, first started coming out in the early 70s, and they needed some kind of squared off number for a reference that wasn't too far away. So that's kind of what we stuck with. January 1st, 1970, the number of seconds since January 1st, 1970. And in this case, this is the number of nanoseconds since January 1st, 1970. So if you count 9 numbers and then you've got the number, and then put the decimal there, that's the number of seconds since the epoch. Let me try it again. There you go. It's a few seconds past. So this is probably the second marker. I don't know. I'd have to count. So number of seconds or nanoseconds since the epoch. So basically, if I say this current time, it starts here, and this current time is when my algorithm stops, I can time the whole thing. So total milliseconds is that divided by 1,000,000. Oh, this is a nice tip here. Instead of putting zeros like that, and then having to count like, oh gosh, what is this, 1,000,000? Is this 100,000 or what? Python allows you to do these little underscores in the middle of a number, and that does not change the value. In case if I wanted to be chaotic here, I could put underscores all over and it would not change the value. But this is sort of like having commas in written numbers. Okay, so this is 1,000,000. So total milliseconds is talk minus tick divided by 1,000,000. So I know that talk is always going to be bigger than tick, so I don't have to worry about negatives. So that's the total milliseconds that it took for this algorithm to run. Okay, so I'm doing a linear search on a random integer that I know is in the array or in the list. Where is it in the list nums? And what is nums? Like I said, it is. Or I don't think I said this already. Sorry. It is all the numbers I for I in range. So all the numbers from 0 to 10 million. So that's a big old list. It's a big old list I created with list comprehension. All right, and then what it does is it adds to times. What is times? It's an empty list so far. So it appends to the end the total milliseconds. So the timing of this thing. So how long did it take in milliseconds? Add that to the list and then print it as well with an F string. Print, this took blah, blah, blah milliseconds. So then print, on average, this took, I can do statistics mean on this list. What's the average time, the average of the list of times that this process took. Okay, so I'm doing a linear search. I'm doing a linear search of some number between 0 and 10 million in the list of numbers between 0 and 10 million. Let's run it. Enough talk. Let's see it happen. Okay, so between 0 and 10 million, it's taking about a second. That one only took 32 milliseconds. That's weird. This one took about a second. So these are probably towards the end of the list. The ones that are shorter, just so happens the needle is towards the beginning of the list. Okay, so it's linearly checking all of the items in the list. And also linear refers to it scales up linearly. As I make my list bigger and bigger and bigger, the amount of time it's going to take is going to scale linearly as well. Okay, so this might take a good while to get to 100. So I'm just kind of going to let that run as I explain binary search. So binary search is a much better algorithm. It's a much better step-by-step process of how to find the needle in a haystack. So you take your haystack. Remember, the haystack is sorted, so it's not really a good haystack. But the haystack is sorted. And instead of looking at the very tip, because it's unlikely that your number is going to be the very first number. So instead of looking at that very first number, you cut it in half. You cut the haystack in half. Because you know that one side is going to be the small numbers, and the other side is going to be the big numbers. And then you check. Is my number smaller than this middle part? The middle number in this list? Is my number smaller? If so, we don't need to worry about the big half. If it's bigger, though, we don't need to worry about the small half. So we get rid of half in one check. We reduce the number of checks we need to make by half after one check. Then you take that smaller half and you just do it again. So now you take the middle of that smaller half and you compare it to the needle. Is my needle going to be in the big half or the small half? And then you throw out the wrong one. So you keep dividing the haystack by 2 every time. So really, this scales logarithmically. It's a logarithmic algorithm. It has logarithmic time complexity. We can talk more about what that means later. But as the number gets bigger and bigger and bigger, really, really big, the number of checks you have to make doesn't really get that big that fast. Okay, so it scales nicely as well. That's another thing we can say. So at really, really big in really, really big lists, this is a really nice searching algorithm. The number of checks is pretty small. Big lists. Okay, so here's how the implementation breaks down. So I start by naming high, mid, and low. These are indices. So the high index is the very end, right? The length -1. So that's the last index. The low starts at 0, and the mid is half of the high. And that's an integer division. This is a floor division because I can't have a fractional index. So while true, this is a little risky of an implementation. I've seen several implementations of binary search on the internet. This one, I decided that I can just do while true to make it a little simpler because I know that eventually it's going to hit the actual needle and then return the actual needle. So if the needle is not in the haystack, then that might not happen, and this condition needs to be different so that it actually breaks out of this while loop. So first it checks, is the very middle stalk of hay, is that the same as the needle by happenstance? Did we happen to get a needle that's right in the middle? Hooray, we found it, return it. That's the index of your needle, you're done. That's probably not going to happen first try. So then you check a different condition. Else if the haystack at the middle, the stalk of hay in the middle is smaller than the needle, meaning the needle is in the bigger half. The needle is in the bigger half. Then you remove, let me make that. There we go. Then you remove the lower half. Okay, so how do you remove the lower half? Well, you change where low is located. The low number is no longer at the beginning of the array, 0. You move it to just above the middle, and then you can after that move the middle to between the high and low. Okay. If the needle ends up being smaller than the mid, so it's in the small stack, then you can get rid of the high stack. How do you do that? You move the high number down. You move the high number down. So high equals mid minus 1. That's a 1, not an L. Okay. Yeah, so let's see how it goes. So let's replace linear search with binary search. And yeah, on average, this took 868. So we're doing the exact same parameters, exact same numbers, 10 million numbers, and a random number in 10 million. So I'm trying to find that number. Let's run it. That took 800. Oh, it's all the way down. It's all the way down. It took 0.02 milliseconds to do each one on average. Yeah, so look at that. It took barely anything. So these are my numbers. Oh, wait. That's really interesting. So these are some numbers. Maybe those are numbers from this binary search. So sometimes timing your code, it kind of is weird, especially on Replit. By the way, especially on online editor and online running environment where you only have half of a virtual CPU. There might be some other processes clogging up the system, or maybe the web traffic is slower at a certain time. So that's kind of weird. That sometimes, kind of unpredictably, it can do weird stuff. Let me kind of run this again. Clear the REPL. There we go, and run it again. Yeah, on average, it took a very, very short amount of time. So maybe that was from the last output. That was kind of weird. Okay, so yeah, binary search scales up really, really, really well. And if I went bigger than 10 million, I actually tried it, and Replit doesn't like it, or maybe it's Python that doesn't like it. It can't hold a big list that's that big. Yeah, so binary search scales up really, really nicely. In fact, if you take the logarithm of the number of numbers with base 2, that's approximately the number of checks you need to make. Okay, so we'll talk about the math behind that.